Good morning, everybody, and welcome to Ceramic Storytime with Sue. I'm Sue McLeod, and today I'm going to be sharing with you a presentation I gave at NCECA conference in 2018 called Understanding Cone 6. So I'm just going to give you a minute to join me live, and if you're here live, then please say hello in the comments section. I'm just gonna make sure that I can see me live in Facebook. Okay, it looks like I'm live. So yeah, if you're here today, please say hello. Let me know where you're joining me from this morning. And so I'm going to be reading the presentation that I gave. And if you want to follow along, you can go to bit.ly, that's bit.ly/understanding cone 6, all one word. And then that will take you to the post, pardon me, and so you can follow along as I'm reading. Hello, Lynn from Winnipeg. Hello from Calgary. And so another thing is that at the bottom of the description on this post, there's a link that you can click because I can't actually see your name when you're commenting unless you give this program BeLive permission for me to see your name. So if you want to ask questions and comment and you want me to see your name rather than just Facebook user, then click the link. Let me just post it to the comments, and you just click the link and it just gives you permission. It'll take you to a thank you page, but then you just come right back to this page and then I'll be able to see who I'm talking to. So let me just clean up my screen here. I'm going to hide this title and then I'm going to share. I'm going to share my screen. Okay, so this is the post on my website that if you go to bit.ly/understanding cone 6, it's scrolling across the bottom of the screen, and then that will take you to this. You can download it as a PDF if you like, just by clicking this link here and then enter your email address, and then it will send you a copy of this that you can keep in your files. And then this video at the top is from my actual original presentation at NCECA. And so it's just my voice talking over slides. But this is going to be a little more interactive where you can ask me questions as I go along. So feel free to do so. We're talking about glaze chemistry today, which is my absolute favorite subject. I love talking about this. And I haven't been talking about it as much recently. I've been talking a lot about specific gravity and mixing glazes from scratch. And so I'm really excited to talk about glaze chemistry. Okay, hello from NH, New Hampshire, I assume. Joan from Texada. Is that Texada Island? Let me know. That's close by if so. Hello from Michigan. Isabel, hello from Quebec City. Hi from Wales. Awesome. Thank you all for joining me here today. So as I read through this, feel free to post any questions that you have. And I am happy to answer them for you. So, understanding cone 6, as I was saying, this was a presentation that I gave at the NCECA conference in 2018, Pittsburgh. So on March 15th, 2018, I gave my first ever NCECA talk. I was part of a panel discussion called Glazes Without Borders, moderated by Matt Katz. And Matt Katz was my teacher, where I learned all this glaze chemistry. So he invited 3 of his students, so Chiara Matos and Peter Berg and myself. We had all taken all three of his online courses through Alfred University. So he invited us because we were actively like using what we had learned in his classes in real life. So he invited us to do these research projects and then present them at NCECA. So Chiara gave a talk about copper as a flux. So the copper's role in a glaze as a flux, as a melter. And then Peter did a talk about copper leaching and glaze durability, where they made a bunch of glazes with different levels of copper, different flux ratios, and fired them at different temperatures, and then sent them all to a lab to be tested for copper leaching. And so he presented his findings on that, which are really interesting. And so if you want to watch the full hour-long presentation with all three of our presentations, then there's a link here that you can click, and so it's all on NCECA's YouTube channel. So you can check that out. The other two talks are very, very interesting as well. Okay, and then this is just the original video. And then here is where you can download this post as a PDF. And then this is the beginning of my presentation. Okay, just making sure everything's good. Facebook kicked me off last week, so hopefully this goes well. Okay. Hi, everyone. I'm Sue McLeod. I live in Victoria, British Columbia, where I work full-time as the ceramic studio technician at the Art Center at Cedar Hill. So I no longer work full-time. I work part-time now, but I still am a technician at the Cedar Hill Art Center. I also teach glaze workshops on the side, and in my spare time, I make pots and test lots of glazes. I first started working with clay in 2008 at Kootenai School of the Arts in Nelson, BC. At that time, they offered a 2-year diploma in clay. In first year, we didn't make our own glazes, which sort of sucked, but was sort of fine because I was still making pretty crappy pots anyways. But then in second year, we had a glaze technology class where we learned a bit about glaze materials and we tested hundreds of glaze recipes. That class totally changed my relationship with ceramics. In high school, chemistry was my favorite subject. I almost pursued it as a career, but I got distracted and dropped out of college to travel the world. I never really identified it as an artist. I just always liked making things. Somehow, though, I ended up in art school, which was a bit weird for me until I got to glaze class. The science made the art so much more exciting. I was really enthusiastic about learning how to mix my own glazes because the process just looked so scientific. You wear a mask, which made it look dangerous and important, and you weigh out materials on a triple beam balance scale. It seemed so precise. It seemed so precise and mathematical, which really attracted me. By the time I graduated, I had a binder full of glaze recipes and several boxes of test tiles. I had a good understanding of how to mix glazes and change their colors, but I still didn't really understand how all the materials worked together. Next thing I knew, I was out on my own and using my favorite glaze recipes from school, but they happened to be super runny at cone 6. So every firing was a gamble with fingers crossed that they didn't run too much. I became very proficient with a bench grinder and a Dremel tool. And then I ran into more problems, like a kiln load where every pot with a certain glaze combination was cracked right in two. I was losing so many pots, wasting so much time, and not really learning anything. What were my options? Go back to school, find new glazes. But I loved these glazes, and I had so many of them. I just need to learn how to adjust them. I know. I'll ask the thousands of potters on Facebook what to do. If any of you have ever asked a technical question in one of the ceramics Facebook groups, you might know what I'm talking about here. I posted a photo of my kiln load of cracked pots and asked what I should do. I received exactly 65 comments, each telling me to do one thing or the other. Seriously, lower the lithium, add some silica, remove some silica, cristobalite, quartz inversion, change the heating rate, change the cooling rate. Don't open the kiln so soon. Compress, compress, compress. I was grateful for everyone trying to help, but it got me nowhere. I didn't know anyone. Who should I listen to? I was more confused than ever. It was a very short time later that I saw a Facebook post for Matt Katz's very first online Intro to Glazes course through Alfred University. It was a little pricey, especially when converted to Canadian dollars, but I did the math and quickly realized how much it was costing me to stay in the dark. I signed up and the course completely blew my mind. It answered all my questions, plus a gazillion questions I hadn't even thought of. That was in 2014. I have since taken Matt's Glazes 2 class, his clay bodies class, and I'm anxiously awaiting his next course offering. Fast forward to the present, thousands of test tiles later, I'm going to present to you the research that I did on Cone 6 glazes, the relationship with Stull's glaze map, and how we can use Stull's map to predict glaze behavior at Cone 6. Hopefully some of you are familiar with Stull's map or chart, which is pictured here. This is Stull's chart. If you're not, I recommend taking one of Matt's classes. Stull's map, written in 1912, by the way, is a document that allows us to predict glaze behavior based on the chemistry of a glaze formula. In order to look at the chemistry of a glaze, we need to calculate the unity molecular formula, or the UMF, of a glaze recipe. The UMF takes all the glaze materials in a recipe and breaks them down into the number of molecules or moles of each of the elements in our glaze. Every glaze will contain glass formers, and every glaze will also contain fluxes. Fluxes are required to bring down the high melting temperatures of the glass formers. The glass formers are silica, alumina, and boron. Examples of fluxes are sodium, potassium, magnesium, calcium, etc. If you were to look at the periodic table of elements, the fluxes are found in the first two columns on the left, plus zinc, which is over on the right, but zinc's also a flux. What the UMF does is it puts the glass formers into proportion with the fluxes. Chemistry is all about proportions of one element to another. Once we know the UMF of our glaze recipe, we can plot it on Stull's map, and we will be able to predict how our glaze is going to behave even before we put it into the kiln. So this is Stull's map here. So you can take any glaze recipe, convert it to the unity molecular formula, and then you can plot it on this map here. So that's just what I was referring to there. So you might be wondering how to calculate the UMF of your glaze recipes. There are various glaze calculation softwares out there where you can just plug in a glaze recipe and it calculates the UMF for you. I recommend using the website glazy.org. It's free, and you can not only calculate the chemistry of your glazes, but you can also upload photographs and share them with the ceramics community. It's also a great resource if you're looking for glaze recipes. Glazy.org will also take your glaze recipe and plot it onto Stull's map for you. So when you enter a recipe into glazy.org, there's a little Stull chart like this one here, although it's colored. So it looks a little bit different, but so glazy.org will calculate the UMF of your recipe, and then it'll put a dot onto the Stull chart to show you where it falls on the chart. Stull's map plots silica levels on the x-axis and alumina levels on the y-axis while keeping the flux ratio constant. Flux ratio? What's a flux ratio? Well, there are two different kinds of fluxes. There are primary fluxes and secondary fluxes. The primary fluxes, also known as alkali metals or R2Os, are found in the first column of the periodic table. They are lithium, sodium, and potassium. The secondary fluxes also known as the alkaline earths, or ROs, are mainly found in the second column of the periodic table. They are magnesium, calcium, strontium, barium, and zinc. And I mentioned earlier, zinc isn't in that second column of the periodic table. It's over to the right, but zinc is also a secondary flux. The two types of fluxes work together. The primary fluxes get the melting started, and the secondary fluxes keep the melting under control. When looking at the UMF, the sum of the fluxes will always equal 1. And so if you want to think about, my favorite way to think about the primary fluxes versus the secondary fluxes is kindling versus like throwing logs on the fire. So the primary fluxes are like the kindling. So they burn really fast. And so they move really fast. They're really reactive in the kiln. And so they really get the melting of the glaze started. And then the secondary fluxes are like throwing logs on the fire. They have more like lasting power. So they keep the melting going up until the top temperature of your glaze firing. And they keep it so that if it was all just primary flux like sodium or potassium, then it would just like melt really, really fast. And so the secondary fluxes kind of act like a stabilizer, stabilizing the primary flux. And so that the melting doesn't happen too quickly. So it helps us to have longer firings where it doesn't like reach temperature in an instant and then all of a sudden it's way too melted. So that's kind of the difference between the primary and the secondary fluxes. The primary fluxes are like the kindling to start the fire, and then the secondary fluxes are like logs that you put on to keep the fire going. So I just wanted to throw that in there because I find that that helps me to understand like what the difference between the two are. Okay, so then we can further break down the fluxes and look at how much primary flux we have compared to how much secondary flux. This is called our flux ratio. It's generally written as the ratio of R2O, which is the primary flux, to RO, which is the secondary flux. Historical and contemporary research have shown that a flux ratio of 0.3 to 0.7 contributes to the highest durability of a glaze. As you can see, this is the flux ratio that Stull used in his research, 0.3 moles of potassium to 0.7 moles of calcium. So let me just go back to Stull's chart here. So here we have our primary flux is potassium and our secondary flux is calcium. And then we have 0.3 moles of potassium to 0.7 moles of calcium. And so that's the flux ratio here. So Stull in 1912 was working with a 0.3 to 0.7 flux ratio, and he was firing to cone 11. Okay, so with a consistent flux ratio, all he did was vary the amounts of silica and alumina to create glazes at all points on the map. So, let me go back to the map. So all points on this map, the only variables are the silica, which are on the x-axis, and then the alumina are on the y-axis. So the fluxes always stay the same. And the only thing, so you can make a glaze recipe for any point on this map by keeping the fluxes the same and then just changing the silica and alumina levels. So that is what Stull did originally. So every little circle that you see on this map represents a glaze recipe that he tested. Sorry, I have to keep going back and forth to show you the pictures. Okay, where was I? Here. So what does Stull's map tell us? Stull discovered that with a consistent flux ratio, a glaze's surface quality, glossy, matte, crazed, or underfired, is determined by the glaze's silica and alumina levels and their proportion to each other. Stull predicts that glazes will be matte when the ratio of silica to alumina is 5 to 1 or below. As the silica to alumina ratio increases, the glaze becomes glossy. Stull refers to glossy as bright on the map. And Stull predicts that glazes will be underfired at a silica to alumina ratio over 12 to 1. Stull refers to underfired as devitrified. Stull also predicts crazing, shown by hatch marks, at low silica and alumina levels, the lower left-hand side of the map, as well as at high silica levels, the right-hand side of the map. Stull's research was done at Cone 11. So let me just go back to Stull's chart here. So here is where basically this is the matte. Hopefully you can see my arrow here. So this is the matte section here. So anything above this line he found was unfused or underfired. And then we've got this line here. So this diagonal line represents the 5 to 1 silica to alumina ratio. And then we've got the glossy section in the center, which Stull referred to as bright. And then down here, this is like the 12 to 1 silica to alumina ratio line. And then below this, he's saying these are devitrified, which I'm calling them underfired. And then the hatch marks represent where Stull found crazing. So with his clay body, because crazing is always a relationship between your glaze recipe and your clay body. So with his clay body, he found crazing below this curve here. So these were Stull's results. And then I'm going to show you. So I recreated Stull's map at Cone 6. And then I plotted my results onto his map to see whether they correlate with each other. So boron. Since I was working at Cone 6, I couldn't rely on the fluxes alone to sufficiently melt my glazes. I needed to include some boron, which is a low temperature glass former. This chart, so this is Matt Katz's research on boron, where he found that the ideal boron level for every temperature. So at Cone 10, our glazes will melt with feldspar, like primary and secondary flux alone. But as we start lowering the temperature, then the glazes kind of struggle to melt. So when we add boron, which is a low temperature glass former, then that brings the melting temperature down. And so you can see down here on the x-axis, we've got the UMF of boron. And then on the y-axis, we've got temperature in Celsius. And so right here, this is where Cone 6 falls. It's at like 1200 and something Celsius. And so we're at like between 0.1 and 0.2 boron by UMF. And so right here is where Cone 6 falls. And so the ideal boron level for Cone 6 glazes is around 1.5. And so if you want to see Matt's research on boron, you can just click this link here. That will take you to his explanations of how boron affects melting and durability at lower temperatures. And so based on this data, I chose a consistent boron level of 0.15 for all of my glaze tests. And then these are the results. So these are all the tests that I fired to Cone 6. For the project, I created 2 separate Stull maps where I mixed a glaze sample for each point on the map and fired them all to Cone 6. Here are the tiles arranged as if they were on Stull's map. Each row represents a constant alumina level, and the silica increases from left to right. So, so this chart here, so you could imagine all of these test tiles are a point on the map. We've got our boron level is at 0.15 boron, and then our flux ratio is 0.3. I used sodium. So Stull, in his original research, he used potassium as his primary flux. I used sodium, 0.3 sodium to 0.7 calcium. And then here, this row of test tiles all have an alumina level of 0.3, and then 0.4, 0.5, 0.6, 0.7. And then I did another map where I used a different flux ratio. So all of these test tiles on the right have a 0.2 to 0.8 flux ratio. So 0.2 moles of sodium, 0.8 moles of calcium. They all have 0.15 moles of boron. And so these are, again, 0.2 alumina down here, 0.3, 0.4, 0.5, 0.6. So then what I did was I took my results and I studied each test tile and decided whether it was matte, glossy, underfired, crazed, all of those things in between matte and glossy, satin, that sort of thing. Getting ahead of myself here. So map number 1 on the left. I think I already explained all of this. Yes. So these are my results. So I took each of these test tiles and kind of color coded them and plotted them on Stull's chart here. And so these are my findings. It's a little hard to interpret my results just by looking at photos of test tiles, so I coded all of the data and plotted it on Stull's original map. I looked at each individual tile and decided if it was matte, semi-matte, glossy, underfired, crazed, crawled, or shivered. Here you can see the various trends that resulted at cone 6 and how they relate to Stull's map. So here's 0.3 to 0.7. So all the red circles are glossy. All the yellow circles are kind of, I couldn't decide if they were glossy or matte, or if they were kind of like dull glossy. I called them semi-matte or semi-glossy or satin. I mean, some of them I'm sure would be considered satin. And then the green circles are matte. And then we've got some crazing, and I'm going to break all of this down in the future, so it's going to look much clearer. And so we've got 0.3 to 0.7 on the left, 0.2 to 0.8 on the right. And so it's interesting, and I'll describe the differences between the two flux ratios in a minute. So the glossy section. To make the results more clear, here is map number 1, 0.3 to 0.7, showing only the glossy results. Notice how they follow the general pattern and shape of Stull's original map. So these were my physical glossy results. And so they all fall within Stull's bright glossy section here. So they're like shifted a little to the right from what his results were probably. But like the general pattern is the same. So all the glossy results kind of congregate in one section of the chart. And then the matte glazes. So this is map number 1 again, 0.3 to 0.7, showing only the matte glaze results. This left-hand side of the map is where you will find true matte glazes. So all of these green circles represent where all the matte glazes fell. And as you can see, they also follow the patterns of Stull's prediction here. True matte glazes are fully melted crystals growing in a glass. This is as opposed to underfired matte glazes that are only matte because they haven't melted yet. Often, these are underfired glossy glazes. So when you underfire a glossy glaze, then it can come out of the kiln appearing matte. And sometimes you can't tell the difference if you haven't tried firing it to a hotter temperature. So if you have a matte glaze and you fire it hotter and it becomes glossy, then it was an underfired glaze to begin with. A true matte glaze fired hotter will run. So it will stay matte, but it'll be a runny matte glaze. A properly formed matte glaze will be matte at any temperature. And there are other ways to create a matte glaze aside from the silica to alumina ratio, like aside from plotting on Stull. And adding titanium is one way, where you have titanium crystals growing in the cooling cycle, which can create a matte glaze. So this is not the only way to create a true matte glaze is through Stull. But yeah, that I digress. I just wanted to mention that you can also have a matte glaze that is not underfired, that falls into the glossy section of Stull, and that is usually because of something that's crystallizing in the cooling cycle, which is oftentimes titanium or rutile. So from a functional standpoint, you want to avoid underfired glazes because they are unstable and will break down over time. A glaze only becomes durable once it melts into glass. To make a true matte glaze, Stull found that you need a low silica to alumina ratio, generally 5:1 or lower. Look at the hard diagonal line of green circles that moves straight up the line that Stull drew. So I'm referring to these circles here. They go straight up that line on Stull's original chart. This is the 5:1 matte line. My results line up exactly with the research that was done over 100 years ago. Science. Very, very cool. All glazes on this line have a silica to alumina ratio of 5:1. As soon as the silica to alumina ratio went above 5:1, then the glazes were no longer matte and started to become glossy. And so kind of in between matte and glossy, I was getting some semi-matte or satin surfaces. So Stull's matte can be used to predict a matte or glossy surface according to the silica to alumina ratio. So here's that 5:1 matte line. So these are the actual test tiles that fall on this line here. These tiles represent the 5:1 matte line that I showed you on the last slide. The tiles on the far left contain, the tile on the far left, so this tile here, contains 0.3 alumina and 1.5 silica. It would be plotted on the lower left-hand corner of Stull's map, where it is predicted that there will be crazing. As you can see, there is crazing. This sample is also running because the silica and alumina levels are so low that it's overfired at cone 6. So you can see that these four tests are all running. So you can see the drips on the bottom. So these are matte glazes that ran because they are true matte glazes, crystals growing in a glass. And then these are not running here. So as we move up the diagonal 5:1 line, increasing the silica and alumina proportionately, a couple of things happen. The crazing is reduced until there is no crazing, and the running is reduced until there is no running. If we keep moving up the line, eventually the glaze dries up as it has too much silica and alumina to melt at cone 6. So this tile here is underfired, so it just hadn't even melted yet. And I determine a test tile is underfired. Usually there's a drip. So when you dip a test tile into the glaze and then you pull it out and kind of shake it off, there's usually a drip on one side. And if that drip is still there after the firing, if I can still see evidence of that drip and it hasn't like melted and smoothed in with the rest of the glaze, then that's how I decide that test tile was underfired. Just checking the comments. Everyone's saying hello. Thank you all. No problem for being late. This is being recorded and of course will remain in the Facebook group and then also be posted all the other places as well after this. Okay, so now let's get into the underfired results that I was just talking about a little bit. So the results also show that there is a limit to how much silica and alumina a glaze can contain and still melt at a specific temperature with a specific flux ratio and a set boron level. So you have to remember that all the tests on this one map have the same flux ratio, 0.3 to 0.7. They have the same boron level, 0.15. So the only thing that is changing is the silica and alumina levels. And if you think about it, the reason why we add fluxes to our glazes is to reduce the melting temperature of silica and alumina, which both have very high melting temperatures. I believe silica melts at around 3,000 degrees Fahrenheit and aluminum melts at 4,000. So it's like cone 42 is the temperature that alumina will melt at by itself without any fluxes. And so we add fluxes to bring down the melting temperature. But if we keep the fluxes the same and we're increasing the silica and or alumina, then eventually there's just not going to be enough flux for that glaze to melt. And so that's why we get these underfired results up at the top here. So at 0.7 alumina, all of these were underfired. And then over here at really high silica levels, these are all underfired as well. And then the map looks fairly similar, just a little bit different at a different flux ratio. So on both maps, when the silica to alumina ratio was above 12 to 1, the glazes were underfired. This behavior was also predicted by Stull, where he calls them devitrified. I also found there to be a max alumina level above which the glazes were underfired. That level changed according to the flux ratio. On map number 1, 0.3 to 0.7, the glazes dried up at 0.7 alumina. And then on map number 2, the glazes dried up at a lower alumina level of 0.6. This is because at 0.2 to 0.8 flux ratio, the glazes have less R2O, so they have less of the primary flux, which is the really reactive flux that gets the melt going. And the primary fluxes are super powerful, so it has less primary flux, which is why we're getting underfired results at a lower alumina level than with the 0.3 to 0.7, where we have more primary flux. Notice how the pattern of underfired is almost identical on both maps. The shape is the same, it just shifts on the map according to the conditions of what you're testing. If I were to increase the firing temperature, the whole pattern would kind of move upwards. So it would, if we increase the firing temperature, then we could potentially have more silica and alumina and still have a melted glaze. So now we're going to talk about crazing and my findings with crazing. So there are some very interesting trends with regards to crazing and thermal expansion. Crazing results from the relationship between a specific glaze and a specific clay body. Stull's map was created based on his results with his clay body. These are my results with my clay body, which was Plainsman M340, just to let you know. Keep in mind that your clay body may give different results as well, but the general patterns are the same. So you could make this exact same glaze at this point here where I had crazing, and based on your clay body, you might not have crazing in that spot. So just keep that in mind. Like, these are not hard and fast rules, especially when it comes to thermal expansion. When your glaze has very low silica and alumina levels, you're likely to get crazing. As the silica and alumina levels increase, the crazing starts to disappear. So down here, we've got low silica levels are the left side of the map, and then low alumina levels are the bottom of the map. And so you can see that the low silica and alumina levels are where we find the crazing. And then again, over here where the silica levels are really high, we also find crazing over there. If you have a crazed glaze and you only increase the silica, you can move out of the crazing region, but you would then also be changing the silica to alumina ratio. So say you're over here, hopefully you can see that. Say you're over here, you could just add silica and you would move to the right on the chart, and you would move potentially out of the matte region and into the glossy region. So you don't want to change the surface quality of your glaze. You want to keep your glaze the same, but just get rid of the crazing. So a better way would be to take your crazed glaze and increase the silica and alumina so that their ratio stays the same, and you will move out of the crazing region while maintaining the surface quality of the glaze. Now let's look at the far right-hand side of the map, the high silica region. Map number 2 has some, and map number 1 has quite a bit of crazing in this region. So that's over here, where Stull also had hatch marks, which represent crazing. This is because unmelted silica has higher thermal expansion than melted silica. So these underfired tests are also crazed. So if you think about it, so unmelted silica has a higher thermal expansion, and then once it melts, then the expansion goes down. And so when you have too much silica for the glaze to melt, then there's a chance that you're going to also have crazing, just because of that difference with silica has different thermal expansions based on its state, basically. And the last most interesting thing to notice is that map number 2, 0.2 to 0.8, has a significantly lower number of crazed samples than map number 1. So these blue X's are all the crazed samples. I did the same number of tests for each map, and so you can see that there's less crazing on with a flux ratio of 0.2 to 0.8 than there is with a flux ratio of 0.3 to 0.7. Where was I? The reason being that sodium, which is the R2O flux, the primary flux, has higher thermal expansion than calcium. So here we've got 0.3 moles of sodium for every 0.7 moles of calcium. Sodium has higher thermal expansion than calcium. So over here, when we replace 0.1 moles of sodium with 0.1 moles of calcium, so we're basically lowering the sodium by 0.1 and then raising the calcium by 0.1. So we're replacing a higher thermal expansion ingredient with a lower thermal expansion ingredient, which reduces the crazing, like magic or science, chemistry. So in conclusion, well, actually, let me just finish reading this part here. So these 2 test tiles are from the exact same point on the Stull map. So we've got 0.2 to 0.8, 0.3 to 0.7, 3 silica to 0.5 alumina. So these are both on at the same point on the Stull chart, but they just have a different flux ratio. The 0.2 to 0.8 sample is not crazing, and the 0.3 to 0.7 sample has a little bit of crazing. So this tells us that another way to get rid of crazing is to adjust the flux ratio, lowering the R2O flux and increasing the RO flux. So 2 ways to get rid of crazing would be to increase. So if you're in this section here where your silica and alumina levels are quite low, then you can move up and to the right by increasing both your silica and alumina while keeping the proportions the same, and move out of the crazing region. Or you can adjust your fluxes, bringing your R2O down and your RO up, and that could potentially also eliminate crazing. So there are many ways to kind of solve these issues, and you can try all of them. If you're having crazing issues, then that's something you can play around with the chemistry of your glaze formulas and see if you can fix it. I love that. Not magic, but science. Yay, chemistry. I know. It seems like magic, but when it's repeatable, that makes it science. So here we go. Stull's map at cone 6. So here's my conclusion. The results from this research show that we can use Stull's map to accurately predict glaze behavior at cone 6. Stull tells us if our glaze will be glossy or matte, crazed or underfired. This leads me to believe that Stull's map could accurately be used to predict glaze behavior at any temperature, provided your glaze is properly composed to melt at that temperature. So yeah, so generally when glazes kind of fall out of this pattern, it's usually because the flux ratio is completely different than what Stull used for his research. So say you have like a 0.7 to 0.3 flux ratio, you might get completely different results. I haven't tested it. These are the tests that I did at cone 6. So I can kind of I learned all this stuff, and then I fired samples and I kind of proved it to myself by like seeing the results come out of the kiln, seeing the difference between the two different flux ratios, seeing the difference between all the silica and alumina levels. It really solidified what I had learned taking Matt's classes about the UMF and Stull and everything. So I definitely recommend, like, if you are learning all of this stuff, do some tests. And what you could do is let me scroll up here. So you could just do one row of the Stull chart where you start at one point on the left. Okay. So say you want to test like 0.4 alumina. So you can create a glaze recipe that has 0.4 alumina and say 1.8 silica. So you're creating the test on the very far left. So you have as little silica as you can possibly get into your glaze recipe at 0.4 alumina. So you mix that recipe up, dip a test tile, and then you incrementally add silica to move along the x-axis. And so you can make a recipe for each point along the x-axis at this 0.4 alumina level. And then you're going to see for yourself, and you can choose your flux ratio, but you can see for yourself how adding silica moves out of the matte region through the glossy region and then into the underfired region. And it just really helps to, like, when you see those results, you're like, okay, I really understand how this works now. So that is the end of my presentation. I am happy to answer any questions that you have now, if you want to ask them now, or you could also post into the Facebook group at a later point. If you want to plug some recipes into glazy.org and look at the UMF, check out their flux ratio, check out their silica to alumina ratio. If you have a glossy glaze, see where it falls, see if it falls in that glossy glaze section, especially if you have a matte glaze. If your matte glaze falls into the glossy glaze section, you want to have a look at that, because it could be that your matte glaze is an underfired glossy glaze. And so if it doesn't contain any sort of titanium, that might be something to look at. And I would be happy if you want to post in the group and tag me. I'd be happy to check out your glaze recipes. I just ask that you upload your recipe to glazy.org first, and then post the link so that I can just easily see the chemistry. And the other people in the group, there's lots of people in the group that understand this sort of stuff. So we can all just like look at the chemistry really easily and then let you know what we think about that. Lynn says, if the glaze drip on the side of the test tile is a visual cue for an underfired glaze, is there a visual cue for an overfired glaze? Yes, a runny glaze is an overfired glaze. If your glaze isn't running, then it's not overfired. And there's no, like, overfiring a glaze doesn't really become a problem unless it runs and sticks to the kiln shelf. So you can have over-fired glazes, and you can glaze your pots with over-fired glazes, so they don't really become a problem until they start. Sometimes if they're really runny and they pool in the bottom of, say, a bowl, a really thin-walled bowl, and your glaze pools really thickly in the bottom, then that can cause some issues where it can actually crack your pots. But generally, over-fired glazes aren't a problem until they stick your pots to your kiln shelves. Sarah says, hi, Sue. I'm struggling to find a base glaze at cone 6. How can I take my cone 10 down to cone 6? So one thing you could try is to recreate your glaze recipe by adding boron. So that's basically what I did here. Was I added for cone 6, based on Matt Katz's research on boron, he determined that around 0.15, so between 0.1 and 0.2 boron level is ideal for a durable glaze at cone 6. So you could take your cone 10 glaze recipe, add 0.15 boron, try to keep all the other numbers the same, and then fire that. There's no saying whether it's going to be identical with the added boron, but it's not that much boron, so there's a good chance that you could have a suitable glaze at cone 6 just by adding a little bit of boron. Linda, hi. So if 0.3 to 0.7 is the best durability at cone 10, is 0.2 to 0.8 less durable? Whereas comparing cone 6 and cone 10, apples and oranges on this point. So from my understanding, 0.2 to 0.6 is, and this is based on what I learned in Matt's classes, but 0.2 to 0.8 is just as durable as 0.3 to 0.7, but there's less, because you have less primary flux and more secondary flux, there's more of a chance that your glaze could be under fired. So if you take a glaze recipe and the only thing that you change is the flux ratio, and so you move from 0.3 to 0.7 to 0.2 to 0.8, for example, and you're, like say you're trying to get rid of crazing or something, then you want to just make sure that your glaze is still being melted, because as you could see, let's see, where's my, so under fired, so say here you have this glaze at 0.3 to 0.7 with a 0.6 alumina level, and all you do is change the flux ratio, all of a sudden we're over here and we have an under fired glaze, which would not be as durable as that 0.3 to 0.7. So that's the main thing from my understanding that would compromise the durability of changing that flux ratio. Can the Stull chart predict the temperature needed for the glaze to melt properly? So it can't really predict, like the more testing that you do and you match your results to the Stull chart and you kind of start to see the patterns, then it becomes easier to predict. Like glazes up here are going to melt at a much higher temperature than glazes down here. So you could have a glaze down here that's running, and then as you move up, it stops running, and then as you move up, it's becoming under fired, so it's not melting. So as you increase the alumina or the silica or both, you're essentially raising the firing temperature of that glaze, because you're keeping the fluxes the same. The fluxes always add up to 1. So the fluxes stay the same, but you're increasing the glass formers, which have those high melting temperatures. So you can kind of relatively compare, like, okay, I have a glaze up here that's under fired. Chances are moving it down here is it's going to melt at a lower temperature. Increasing boron. So when I look at a glaze recipe If it doesn't contain any boron, I'm a little skeptical of its melting at cone 6. There are other ways to get a glaze melting at cone 6. And one way is to increase the primary flux and lower the secondary flux, where you have a flux ratio that's around 0.5 to 0.5 or even higher than 0.5. So those glazes are going to melt at cone 6 because the primary flux lowers the melting temperature, but then you're compromising the durability of a glaze. So there's lots of different factors that I consider when I'm looking at a glaze recipe and trying to decide what temperature I think that it might fire to. But you can kind of make an educated guess, I would say. Kate says, for a properly designed semi-matte or satin glaze, what level of temp control is necessary? And or does temp soak matter, or is it just hitting target temperature? So the matte glazes that fall, let's see, where are we? These matte glazes. So the matte glazes that fall over here, they will be matte regardless of cooling cycle. So you can just take your glazes up to your target temperature and let them cool naturally. And these glazes are all going to be matte based on their silica to alumina ratio. It's when you have a glaze that is matte because of titanium, for example, that the cooling cycle really comes into effect. And so if you imagine when we reach our target temperature, all of our glazes are liquids. They're like really thick, syrupy liquids stuck to the sides of our pots. And they're all glossy and transparent. And then as the kiln cools, crystals will form to cause a matte surface. And so those teeny tiny crystals grow and kind of like the difference between matte and glossy is a matte glaze absorbs light and a glossy glaze reflects light. So all of those teeny tiny crystals that form on the surface, they absorb the light rather than reflect the light. And so the cooling cycle isn't going to play a part in whether your glaze will be matte if it falls in this matte region of the Stull chart. But if you have a glaze that is matte because it has a lot of titanium in it, then your cooling cycle is going to play a difference, because I have this glaze that has 4% titanium dioxide. When I fire it at home in my really small kiln, that cools really fast. So it cools in like 8 hours. Then that glaze comes out glossy. But when I fire it at work, where we have these big kilns with thick bricks that take over 24 hours to cool, then all of a sudden the exact same glaze is turning out matte. And that's because those titanium crystals grow during the cooling cycle. So in my little kiln that cools really quickly, there isn't enough time for those crystals to grow. And then in the larger kiln with the slower, like we don't program a cooling cycle, it just cools naturally very slowly, then that it gives those crystals a lot of time to grow. Pardon me. Ginny says, how does repeated dipping, then adding to silica alumina, affect the composition of the original glaze recipe? Just 1 second. So basically, I started with, I think I started with 200 grams. So when I made the very first tile on the left, I started with 200 grams of glaze. So you have to make sure that you're mixing your glaze really well. So before every dip, so I would mix the glaze, the base glaze, I would sieve the glaze, dip a test tile, then I would sprinkle silica on the top. I didn't sieve every time. What I found is if I sprinkle the silica onto like the layer of water that's kind of on the top of the glaze, then it just kind of slakes down. But I always use a high-speed mixer in between. And so as long as your glaze is homogenized, like you are removing a little bit of glaze with each dip of a test tile. Hopefully I'm answering your question. Let me know. So you're removing a little bit of glaze, but as long as the glaze is completely homogenized, you're removing everything in proportion to each other. And the larger your test sample is, the less of a, like the less material you're removing from it. So I guess like it's not perfect because I'm adding silica based on the original recipe that I hadn't dipped a test tile in, but you're just going to generally get like the results are going to kind of show you what adding silica does. And then like when I do testing like this, and then I find a result that I'm interested in working with further, then I'll just mix a batch of that formula and test it on its own without like all the additions and the dipping and everything. And then I will test that. I will fire that to make sure that it matches what I was expecting it to. Stir, stir, stir. Yes, exactly. Okay, Facebook user. Thank you, Sue. This is really helpful and takes me back to when I did more glaze testing. Yes. Linda, this work you've done in conjunction with Stull is truly significant for Cone 6 users. Yes, you're very welcome. I recommend everyone does, like anyone that's interested in glaze chemistry, I highly recommend recreating a portion of the Stull map. Like you don't have to do 50 test tiles like I did. I did these on purpose so that I could present this research at NCECA. But even just doing one row is gonna really give you that visual, like where you can see and hold and feel the test tile and see how changing the silica and alumina levels affects the glaze chemistry. Okay, Kate says these storytime sessions are really terrific. I'm so glad you enjoyed them. If anyone has any other questions, I am happy to answer them. Otherwise, I will let you go, but please post to the group. I would love to kind of help you understand this further. Yeah, and I hope to inspire people to start learning and understanding glaze chemistry, because I just love it. Like it's so, it feels so powerful, especially like if you are struggling and frustrated with your glazes right now, to learn this chemistry and then realize the ways that you can manipulate a glaze formula and get different results. And then you start playing with color. Like all of my test tiles are with no colorant. And then once you start adding colorants, then like this whole world opens up, and you can literally just use chemistry and move around the Stull chart and test things, and you can come up with some really cool glaze results. So I would love it if any of you guys do some of this testing. Please post your results to the group, and I'd love to chat about them with you, because I could talk about this stuff all day long. Okay, so I will let you go then, and I'll see you next week for story time. Bye.